Hi, this is Dr. S, and this is the 16th and final video in my series on reaction rates for Year 13 A-Level Chemistry. In this video we'll look at how to create an Arrhenius graph and use that to determine the activation energy or the frequency factor from given data. So just to remind us from last video, this is what we came up with. We found that we could use the logarithmic version of the Arrhenius equation and marry it up with the equation for a straight line graph. And then if we graph 1 over t against ln k, we get a straight line going downwards, the intercept of which is ln a, and the gradient of which is minus Ea over r. K and T, so the rate constant and temperature, are things that we could get from experiments. We could perform an experiment at different temperatures, measure the rate constant, and then actually do one of these graphs. So that is what we'll do. So let's say we did an experiment to find these things out, and these are the data that came out. So what we need to do in order to do our Arrhenius graph is calculate 1 over t and ln k for each of these data points. So let's do that. So 1 over t, just simply 1 divided by the temperature in Kelvin in each case. So for the first one, you would get 0.00341. For the second one, 0.00330, 0.00319, and 0.00310. Then calculating ln k, so ln is a button on your calculator, so you press that and then put these numbers in. Then you should get minus 2.35 for the first one, minus 1.10, exactly 0, and then 1.10. So now you can see how I've got values for ln k, the y value, and values for 1 over t, the x value. So now what we can do is plot those on a graph. So I have already done this graph. So this is how it looks. So what you can see, that I've plotted the values in the red crosses, and then my orange line is the line of best fit. ln k is the y-axis, 1 over t is the x-axis, and of course there's a break in the axis here. So we have a straight line. Now remember the two things that we can work out from this. It's the activation energy from the gradient and the frequency factor, A, from the y-intercept. Let's do the gradient first. Because I've got quite a nice straight line graph there, and I've got 2 points, the line actually goes through the first and the fourth point. I'm going to use the first and the fourth point to help me calculate my gradient. So if I go back to my data, I'm going to use the first and the fourth point to calculate my gradient. So my difference in y is the difference between the first ln k and the second. So the difference here is 3.45. And the difference in my x value, 1 over t, between the first and the last is 0.00031. Okay, now actually if you look, one of them gets lower and one of them gets higher, so really that means minus 3.45 over that. If you run that through a calculator, you should get an answer of minus 11,129. So let's think about what we need to do with that. Remember that the m is minus Ea over r. So this value is minus Ea over r. So in order to get the activation energy, I need to multiply by r. If I take minus 11,129, multiply by 8.314, then I get an answer of 92,527. Now I've got to be careful here and think about the units. Remember, when we're using the Arrhenius equation, the EA is inputted in joules per mole, so this is joules per mole. We wouldn't normally report an activation energy in joules per mole, so that should be changed to 92.5 to 3 sig figs kilojoules per mole. So we have our value of activation energy from our graph. Okay, right, next thing. If we want to calculate A, we need the y-intercept. Now there's quite a serious problem in using this graph to do that. A lot of students would want to just extend this back to the y-axis, read that off and say, oh yeah, it's 2 point something. But the problem is there's a break in the axis, so you can't do that. And actually, if you look at the scaling here, if I wanted to actually extend all the way back to the y-axis, then my y-axis would be somewhere way off the screen. So what we do need to do in this case is calculate the intercept mathematically. So let's think about how we'll do that. Go back to our numbers here. We can see that the gradient here is minus 11,129. Well, remember, the equation for a straight line graph is y equals mx plus c. I want to find c. So if we rearrange for c, c equals y minus mx. I have my gradient here. M is the gradient, this is the value. So all I need to do is take any value, any corresponding value of y and x from my table and plug these numbers in. Okay, so I could take any of these to do that. So let's say I take this one because it's nice easy because it's got a 0 in it. So c equals, remember lnk was y, so 0 minus m, which is minus 11,129 times by 0.00319. And if I run the numbers there, I should get an answer of my intercept here of 35.5. So that is C. The y-intercept, remember that is LNA. So the last thing is just to change that into an actual number rather than an ln. So remember that the opposite of an ln is an e function. So in order to calculate the actual number of a, what we'd do is we'd do e to the power of 35.5, and that would give us a. And that, hopefully I've got this correct, comes out as 2.62 times 10 to the 15. And remembering that the units of A is the same as the units of K, well K is up here, so I'm going to copy the same units, dm 3 mole minus 1 s to minus 1. So just to summarise what we've done, we've used some experimental data to calculate 1 over t ln k. From that, create a straight line graph from which you can calculate a gradient and an intercept. The gradient can be used to give us the activation energy here, and the y-intercept, which we can calculate, can give us the value of the frequency factor A. I know this is quite complicated, I know it's quite hard. Play it a couple of times if you need to and take it slowly. Try and get yourself some examples and try them. There's plenty in the textbooks. Okay? Thanks for listening to this series on reaction rates. I'll see you for my next one. See you then.